How does it happen? What does it all mean?
Let's find the answer.
How does it happen?
Let's find the answer.
Day 89 of my science trip. That's me at the airport.
I could really use something with wheels right about now. Lugging this heavy suitcase around is a real drag.
What I really need is a simple machine. That's simple, like basic, as in not very complicated. Now that guy has the right idea. Ah well, the journey begins. Every day we do stuff that takes effort and uses energy. All kinds of different things. Some more fun than others. Whatever the activity, using force to move something is called work. From jacking up a car to pulling this block of ice. If we use force to move something great or small, that's doing work. A basic example of work is lifting. These weights are heavy. To lift them, I have to use force, a push or a pull. How far I lift them is distance. In scientific terms, work is a formula. Work equals force times distance. So it's pretty easy to understand. Work is moving an object by using force, and it depends on two factors, force and distance. We've seen that work requires force, but there are really two kinds of force involved. There's the force you exert to do the work, called the effort force, and there's also the force you're working against, called the resistance force. For work to happen, the effort force must be greater than the resistance force. Two common resistance forces are gravity and friction. Take my weightlifting example. Of course, you can see that me pulling up on the weights is the effort force. Here, the resistance force is gravity, pulling down on the weights. Oh, now this is work. Now think of me dragging this ice block around. The resistance force is friction, the heavy block rubbing against the ice. It seems obvious that work is happening all around us every day. But it would be a rough world if we had to do maximum work all the time, right? That's where simple machines come in. Machines make work easier. How? By reducing the effort force needed to get the work done. To do this, simple machines often spread the effort force over a greater distance. Remember the formula for work? Work equals force times distance. If the distance is increased, then the force needed to get the work done is decreased. That's the key to simple machines. The force and the distance can change, but the work remains constant. Let's take a look at 6 simple machines and how they make work easier. Who knows who the guy or girl who came up with the lever idea looked like? But the odds are they were confronted with a basic dilemma. How do I move an object so heavy that using all my strength I can't make it budge? Problems. Somewhere along the line, one of these ancient people here, our scientific ancestors, was inventive. They discovered that if they put a stick under the rock and pushed it down on a smaller rock, they could move the big rock. Brilliant! At the time, they probably had no idea they had created a lever, but this simple machine got the work done. a giant technological leap forward. So let's look at the science behind it. A lever is a rigid bar that turns around a fixed point. Fixed means that the point doesn't move. It stays still as the bar moves around it. The fixed point is called the fulcrum. In this rock example, the small rock is the fulcrum. When the bar, or stick in this case, is leaned on the fulcrum, the effort force down on one end is multiplied up at the other end. This allows it to overcome the resistance force. Here, the weight of the big rock is the resistance force. In other words, using a lever helps you lift the rock. It makes the work easier. One thing about levers that even the cave people probably understood is that the position of the fulcrum makes a big difference. The closer the fulcrum is to the resistance force, the more the effort force is multiplied. That's because the effort force is extended over a greater distance than the resistance force. This is called mechanical advantage, or MA. Mechanical advantage is the number of times that a machine multiplies the effort force. Levers show up a lot in our lives. A seesaw is really a giant lever. The handle of this car jack is a lever. It helps me multiply my effort so I can lift up this car on a hydraulic jack. A hammer pulling out a nail is an example of a lever. Here, the resistance force is the friction of the nail against the board. Rowing oars and paddles are levers. They help us use less force to propel a boat through the water. Don't forget, a lever is nothing without a fulcrum, the point the lever turns around. Can you find the fulcrum in each of these examples? Very good. Time for our next simple machine.